Hello children, today you are going to learn about resolving power of a microscope. Already I have explained about the resolving power. The reciprocal of the resolution is called the resolving power. So it's a property of the microscope. A good microscope should resolve the 2 points on an object which are separated by a very small distance. That is called the D minimum. Okay, if you are using a microscope, the microscope should be a good microscope so that it should resolve the 2 points on an object that should be separated by a very small distance d minimum. So it should resolve the 2 points on the object. That means we are able to see very clearly the distance between the two objects, means it's a high resolving power microscope. Now here D minimum is represent the resolution, that is the distance between the 2 points on an object is represented by D minimum. So that is called the resolution. So lesser the resolution, that is lesser the distance between the 2 points, that means higher will be the resolving power of the microscope. Now in case of the microscope, how to find the resolving power? Well, let us consider an object. Okay, this is an object. It is placed at a distance u, and here beta is a conical angle, and here there is a lens, and here the aperture of this lens is nothing but a, and here you can see that the rays should go straight, but because of the diffraction effect the rays are bending like this. Now here the angle of theta is called angle of diffraction. So this angle theta is called angle of diffraction. Now here you can see the image. Here it's a point size image. And here you can see that image like this. Okay, R0 is the radius of the central maximum. This is the central maximum. You are getting the clear image here. The radius of that clear image or the central maximum is called the spatial resolution, and the value you can calculate using the formula R0 is equal to 1.22 lambda f by a. This is the expression for the central maximum, radius of central maximum. That means it's a spatial resolution. Suppose the value of u is greater than f. Greater than f means if it is equal to f means definitely you will be getting the image at infinity, but here the object distance is greater than the principal, greater than the focal length. So in this case we can calculate the image distance as v. But here in the previous case, in the case of the resolution, we have marked that image distance as f, but in the place of f we have to replace. Here in the place of f, here the image distance is represented by the symbol v, so f is replaced by v here. Okay, in the diagram image distance we have taken as f in case of resolution. So as per this distance, image distance, we are writing the formula for R0 as 1.22 lambda f by a, but here in this case the image distance is taken as v, because the value of object distance is greater than f means at a particular distance we will be getting the image. So that in the place of f we are replacing it by v. R0 is equal to 1.22 lambda v by a. Now the magnification formula m is nothing but it is a ratio of the, what is this? It is a radius of the central maximum to the d minimum, and this is the radius of the image. Okay, and here this is the distance between the 2 points on the object. The minimum distance between the 2 points on an object is nothing but what is the d minimum. So the ratio between these two is nothing but what is the magnification. Okay, next we will see that now d minimum is nothing but R0 by m. Just we are modifying the formula. M is equal to R0 by d minimum. So d minimum is equal to R0 by m. And now we know the expression for R0. We just substitute here 1.22 lambda by a, lambda v by a. This is the expression for R0. And then we know the formula for magnification. M is equal to v by u. We know the image distance and we know the object distance. So using this relation we can find the magnification. So you just substitute to find d minimum, v by u. In the place of m, you just substitute v by u. So if you substitute v by u, this v is getting cancelled and this u it will go to the numerator. So we are having the formula as modified formula as 1.22 lambda u by a. Okay, now d minimum is nothing but 1.22 lambda by a into f. Suppose if the value of u is approximately equal to f, here not that f, here I am just assuming that the value of u approximately, for example, if the focal length of the convex lens what we are using is 10 centimeter, object distance what I am keeping 10.5 centimeter. So it is approximately equal to that focal length. That's why just I am replacing this u by f. Okay, now we are having beta as the conical angle, theta is the angle of diffraction on the object side, and beta value is very small, so we can take tan beta is equal to, see there is a conical angle beta, this is the beta, and here this distance is a by 2, half of that aperture, that is a by 2, and this is beta. From this you find tan beta. So tan beta is equal to, the expression is tan beta is equal to a by 2 by f. This is opposite side by adjacent side. Opposite side is a by 2 and f is adjacent side. Okay, now 2 tan beta is nothing but a by f. Now if the value of beta is very small, means we can write tan beta as well as sin beta as beta itself. So here the value of beta is very small, so we can write 2 tan beta as 2 sin beta, because beta value is very small, so that we can take these two. In the place of tan beta we can write sin beta. So sin beta, 2 sin beta is equal to, already we have found that it is a by f. Here it is a by f. Next, and a is equal to f2 sin. A is equal to f you bring on the other side, so you are having f2f sin beta. And now here d minimum is equal to 1.22 lambda, and then here this f is f I have written here, and then here the value of a is f2 sin beta. This f it's getting cancelled, so we are having 1.22 lambda by 2 sin beta. Next one, the lesser the value of the d minimum, higher will be the resolving power. Both are inversely proportional to each other. So to reduce, how far we are reducing the value of the distance d minimum, that is the distance between the 2 points on an object, okay, that much the resolving power will be maximum. Okay, so to reduce this d minimum, the optical path of the light is increased just by immersing that objective lens of the microscope into the bath containing the oil of refractive index n. So just we are immersing the objective lens in the oil, in a bath containing oil. The refractive index of that oil is n. So we are writing the expression, see here so many derivations are left. The final expression is given as d minimum is equal to 1.22 lambda divided by, instead of 2 sin beta I am writing the 2n sin beta, where n is the refractive index of the oil. And here this n sin beta is called n into sin beta is called the numerical aperture, that is NA. So we can write 1.22 lambda by 2 into this 2 sin beta is n sin beta is written as n sin beta only, it is a numeric, n sin beta is a numerical aperture. So we are writing the 2 into numerical aperture. The resolving power of the microscope is reciprocal of the distance d minimum. That's why you are taking the reciprocal for this, so that you are finding the resolving power of the microscope. So 2 into Na divided by, take reciprocal for the previous expression. So 1.2 Na divided by 1.22 lambda. Rm represent the resolving power of the microscope. RT represent the resolving power of the telescope. Okay, the reciprocal of the spatial resolution is nothing but what is the resolving power of the telescope. So already we have found the d minimum value. Now for that you are taking the reciprocal a by 1.22 lambda f. This is the resolving power of the telescope. RT represent the resolving power of the telescope. It is a by 1.22 lambda f. Okay, already we have found the expression for this d minimum. Now you take reciprocal for this, so you will get a by 1.22 lambda into f. Thank you, children.